Good morning, class. Just give me a second. I'm looking at the quiz I wrote for you guys today, so I'm trying to make sure I remember what I am supposed to be teaching you guys. Okay. 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 I remember now. Hello, everyone. I was just reading the quiz. Okay, so I'm gonna go ahead and get started. I think we have enough people. So we are done with momentum, and we are moving on to a new topic, which is called circular motion. Okay, so we're going to spend about 2 weeks on circular motion. And in particular, we are going to talk about what's called uniform circular motion. So uniform circular motion is motion in a circle with a constant speed. Okay, so you're going around in a circle. Okay, that circle has a certain radius, which I'll call capital R, and you're just kind of going around and around. That's uniform circular motion at a constant speed. There's a number. It's called the period. Arigato. Watashi no namae wa Mr. Pettibone. I just saw some Japanese in the chat. So T is the period. It's called the period. And it is the time for whatever object is moving in a circle to go around once. That's called the period. The time to complete a full circle. Okay. So some examples: the period of the Earth's orbit around the sun would be 1 year. The period of the Earth's rotation around its axis would be 24 hours. The period of the moon around the Earth is about 28 days. So there are different, it's a time period, okay? Now, based on this, we can actually get an equation for the speed. So remember, speed is distance traveled divided by the time it took to travel that distance, okay? So the distance traveled is the distance all the way around the circle, which is its circumference. So the circumference of a circle is 2 pi r. Okay. the time it takes to go around the circle is the period. So this is an expression for the speed in circular motion. It's 2 pi times the radius divided by the period. Okay. The velocity. So remember, speed and velocity are different things. Velocity is speed with the direction of travel. Okay. So the velocity is always going to point tangent to the circle. So wherever you are in the circle, the velocity always points tangent to that. Okay? So that's an important point. This is the velocity at different locations along the circle. So, if you're basically turning, so your velocity is changing. Velocity points tangent to the circle. So that is an important factoid. Okay. One thing I like to do is I like to think about what is the velocity of someone standing on Earth's equator. So if you were standing on the Earth's equator, what's your velocity going to be? Well, because if you think about it, the Earth is spinning, right? So you're going in a big circle that is the size of the Earth's radius, okay? And it turns out that the Earth's radius is 6 times 10 to the 6th meters. 6 million meters is the radius of the Earth, approximately. I have all these numbers memorized, but I have like a rounded version of them memorized so that, I can get ballpark correct answers. I think it's actually slightly less than, it might be like 5.7 times 10 to the 6th meters. I don't know. But that's close enough for most purposes. And then, of course, the time it takes for the Earth to go in a circle is 24 hours for it to complete its rotation. Okay. I'm going to close this window because someone started weed whacking. Okay, that's not going to do for our units, so we have to convert that to seconds. And I know that 24 hours is 86,400 seconds. You can work it out yourself. So the time is 86,400 seconds. That's 60 minutes, or 60 seconds in a minute times 60 minutes in an hour times 24 hours in a day. So that's 60 times 60 times 24. Okay? So then we can plug this into our equation. 2 pi r over the period. Okay? And so we have 2 pi times 6 times 10 to the 6th divided by 86,400. And that equals, so plugging this into my calculator, is 436 meters per second. So right now, someone on the equator is actually whirling around the center of the Earth at 436 meters per second. Now, I find that kind of interesting because the speed of sound is 340 meters per second. So you're actually going at a supersonic speed. Okay. Uh, oh my gosh, hang on. Here it comes. um, and also we should talk about the direction of travel. If you think about it, the sun rises in the east and it sets in the west. So why does the sun rise in the east and set in the west? That's because the earth is rotating in the eastward direction. Okay? The sun is basically fixed, and our perspective is changing because the earth is rotating in the eastward direction. So that's the direction of our velocity. Okay? So it's kind of fun to think about, well, gee, what would happen if the Earth were to suddenly stop rotating? Okay? If the Earth were to suddenly stop rotating, then by Newton's first law, our objects in motion stay in motion. So we would keep moving eastward at 436 meters per second. So probably what would happen is if the Earth stopped is you would go splat against the eastern wall of whatever room you're in. Okay? So that's kind of interesting. We could think about what would happen if the Earth stopped. What would it mean in terms of wind? Basically, the atmosphere of the Earth would keep rotating around the Earth. Even though the Earth itself has stopped, the atmosphere would keep rotating. And so we would basically have a 436 meter per second wind that would knock everything down. And actually, if you had a wind that was that fast, when the air would hit objects, it would compress so much. So basically, if the air is moving that fast, when it hits something, it can't move out of the way and go around it. So it just compresses, and so the air gets really hot when it hits something, and it would get so hot that it would actually light the thing on fire. So basically, everything would burst into flames and get obliterated. Okay? So just some pleasant Thursday morning thoughts for you guys. All right. So are we moving at 436 meters per second? No, we are not. Okay, we're actually going less than that. And so to understand why that is, just let me draw a little picture here. So let's suppose that this is the Earth, okay, and the Earth is spinning, like that. So here's the North Pole, and here's the Earth's equator. Okay. So someone on the equator, if someone is standing on the equator, they're whipping around like that. Okay. All right. But California is not on the equator. It doesn't have 0 degrees latitude. We're like at 45 degrees north latitude. So, California is like right here. So we're moving in a circle that looks like this. And you can see that this circle is actually smaller than that circle. Okay, so our R value is smaller, which means that we're not going to be going as fast. We're moving in a smaller circle in the same amount of time. Okay? You could imagine, what if you were viewing someone standing on the South Pole from outer space? That person would just be slowly turning around every 24 hours. They would just be slowly turning around in place. Another fun thing to think about is what would it look like from the perspective of outer space if you were in an airplane that was traveling at 436 meters per second in the westward direction? So if that happened, you would be going exactly opposite to the Earth's rotation. And so from the perspective of outer space, you would actually look stationary and the Earth would just be spinning below you. Okay? So think about that next time you're on an airplane. If you were in an airplane that was going really fast westward, you're actually not moving. You're just fighting against the atmosphere while the Earth spins below you. It would always be, if it was nighttime, then it would perpetually be nighttime because you're staying in the same location. So you would always stay in the sunlight or in the nighttime. So that would be kind of an interesting thing to experience. Okay. So next thing I wanted to talk about is you might recall that acceleration is the rate of change of velocity. So up until this point in the class, we've sort of interpreted a change in velocity to mean a change in speed. Okay? We've dealt with things that are getting faster and that are getting slower. Okay? But that's not the only way you can accelerate. The other way you can accelerate is by changing the direction of the velocity. Okay? So the direction of this velocity vector is changing as you go around the circle. The size of the velocity vector isn't changing because you have the same speed, but the direction of the velocity vector is changing, okay? So because the direction of the velocity vector changes, you accelerate when undergoing circular motion. Okay? And this type of acceleration, this acceleration due to direction change, has a special name. It's called centripetal acceleration. Not you might have heard the word centrifugal acceleration, and that is a real thing, but it's not something that it's different from what you think it is. Centrifugal acceleration. So we don't talk about it in this class. It's kind of like something you would talk about in college if you took a physics class. So centripetal acceleration. So which way does the acceleration vector point? And it turns out that wherever you are in the circle, the acceleration vector always points to the center of the circle. Okay? So you need to know that fact, that wherever you are, if you're going in a circle, the acceleration is going to point to the middle of that circle. Okay? So I'm going to write that down. It's a key point. So the velocity points tangent to the circle, but the acceleration points to the center of the circle. Okay? There's an equation for the centripetal acceleration. If you take a second year of physics with me, I would derive this equation, but you can't really derive it without calculus, so I'm going to pass on the derivation for today, but I'll give you a formula for centripetal acceleration that you guys are expected to use, and that is A sub c, to indicate its centripetal acceleration, is v squared over r. So speed squared divided by the radius of the circle. And this actually makes sense. So centripetal acceleration is the acceleration you feel when you're on a roller coaster and the roller coaster goes around a bend, okay? Or if you're in a car and the car turns and you feel like pushed against the side of your seat. And so what you can imagine, if you were in a car, what would be the things that would throw you to the side of the car most violently, okay? And I think most of you would agree that the thing that would throw you to the car the most violently is a really sharp turn. So what does a really sharp turn mean in terms of a mathematical variable, okay? A really sharp turn means that the radius of the circle is small. So we can see that because radius is on the denominator, the smaller the radius is, the more violent the centripetal acceleration, okay? So you move in a smaller circle, you're going to get flung against the side of your seat stronger, okay? The other thing is speed. The faster you go in a circle, the more violent the centripetal acceleration is going to be. If you're in a roller coaster, you could be going in a really big arc, a really big circle, but because that circle was at the bottom of a, you do a drop in the roller coaster, and then at the bottom of the drop, you then do a turn. So you've picked up a lot of speed, which results in a large centripetal acceleration. Okay? So that's an important formula. Now we could actually combine this with our formula for speed. So we could see that speed squared is actually going to be 2 squared times pi squared times r squared divided by t squared. And we could plug that in, and we could get a second equation for centripetal acceleration, which is 4 pi squared r over the period squared. So this is expressing the same information, but just in terms of different variables. Okay. So that is the formula for centripetal acceleration, and this is the way that it points. We could do a quick example here using this formula. Let's say a jet is traveling at let's say it's traveling at 436 meters per second. What is the sharpest turn the jet can take? So jets are actually limited in terms of the sharpest turn they can take, not by technology so much as by the people who are inside the jet. Okay? All right. Oh, here it comes again. So if you think about it, the maximum acceleration that a person can handle is 10 times the acceleration due to gravity. I believe we watched some videos at the beginning of the year where the guy passed out under high G training. Okay. So the upper limit of consciousness is around 10 Gs. Okay, and even that only for a short amount of time. G is, of course, 10 meters per second squared. Maybe I didn't watch that video, show you guys that video. I'll have to show you guys sometime. So, all right, for now, just take it as a given. If humans experience more than 10 Gs, they pretty much are guaranteed to pass out, okay? And so G is 10 meters per second squared. So the maximum acceleration that you can undergo without passing out is about 100 meters per second squared, okay? So if we use this equation, A sub C equals V squared over R, we have 100 equals 436 squared divided by R. And we can solve for R. I'm not going to show the algebra, but so we have 436 squared divided by 100. And we get 1,900 meters. This is about 1 mile. This is approximately 1 mile. So the sharpest turn, so if you have a jet that's going at supersonic speeds, its turning radius is going to be huge. It's literally going to, this is about 1 mile. So the diameter of the circle is 2 miles. So the sharpest that this plane could turn without the pilot passing out is about 2 miles. Okay. If you tried to do a sharper turn, the airplane itself could mechanically do it, but the pilot would pass out and then lose control of the plane. Okay, that's kind of interesting. All right. So one thing that we can do is we can sort of we can connect. So connecting energy to circular motion. Okay. So let's do an example of how we might connect energy to circular motion. Okay. So what if we had a roller coaster? So the roller coaster drops. Let's say that the roller coaster drops 75 meters. Okay. And here's the roller coaster cart. And it starts at rest. It goes down this, and it gets to the bottom. And now it has some speed which you could calculate using energy. And then immediately at the bottom of that, it goes into a circle. Okay. So this I can't really draw the perspective here, but this is a drop like this, and then once it gets to the bottom, it goes in a circle like this. So it kind of goes like that. Okay. And the radius of that circle is, let's say, 15 meters. Okay. And what I want to know is what is the centripetal acceleration while you're in this circle. Okay. So the formula for centripetal acceleration is v squared over r. Okay. But then to get the velocity, I have to use energy. Okay. And so to get the energy, we can see that this is a conversion from gravitational potential energy to kinetic energy. So we have mgy becomes 1/2 mv squared. Okay. So I can see that the masses cancel out. And I can see that v squared is g times y. I could take the square root and get the velocity if I wanted to, or the speed, I should say. But then I would just square it again to get the acceleration. So I'm just going to leave it as squared. So I can see that v squared is 10 times 75. Okay. So 750 equals v squared. And then I plug that into here. So I have 750 divided by 15 equals 50 meters per second squared. So that's the centripetal acceleration that the riders would experience at the bottom. Okay. And so that would be quite intense. I think that the most roller coasters kind of cap out at 40 meters per second squared. Okay. So that would be, it would be quite exciting. As I yawn. All right. So that's a type of problem that you're going to encounter on the on today's quiz. Oh, thank you. Someone corrected me. You're exactly right. I forgot about the 1/2. So this should be Thank you. So this should be v squared is 1500, and this should be 1500 divided by 15, so it'll be 100 meters per second squared. So actually that would make everyone pass out. Everyone would be, this turn would be so sharp that you would just pass out. My bad. Thanks for the correction. Okay. So one of the things, so in order to accelerate, okay, in order to accelerate, a force is required. You cannot accelerate without a force. That's what Newton's second law says. Newton's second law says net force equals ma. So if your acceleration is not zero, which is the case in centripetal acceleration, then there's a net force acting on you, okay? So that's from Newton's second law, okay? So the force that makes you move in a circle is called the centripetal force. It's called the centripetal force, and it makes you go in a circle. So I usually think about the centripetal force as like it's a roll. So think about like a play from Shakespeare, okay? Maybe Hamlet. Hamlet is a role, and different actors can play Hamlet, right? Different actors can interpret Hamlet. Similarly, different forces that we know about could be the centripetal force, okay, depending on the situation. So the centripetal force is one of the types of forces that we have already discussed, okay? It could be tension or friction or normal force or gravity or anything like that, okay? So let me give you some examples. What if you have a satellite that's going in orbit and it's moving in a circle, okay? The force that is making the satellite go in that circle is gravity. That gravity is playing the role of the centripetal force in that particular scenario, okay? What if someone on a bicycle is riding around in a circle, okay? If someone on a bicycle is riding around in a circle, then it's actually the friction between the tires and the ground that provides the centripetal force that keeps the person moving in a circle, okay? What if you were in a car and the car does a sharp turn? You get thrown to the side of the car, and it's the side of the car that's, maybe the door of the car is pushing up against you. That push from the door is the thing that is keeping you moving in a circle, okay? And, all right? So in that case, it's actually the normal force from the car door that is the centripetal force. As another example, if you're in an airplane, so you're in the airplane and the airplane turns. When an airplane turns, it's the lift force on the wings of the airplane that allows you to move in a circle. So there's always a force playing the role of the centripetal force that makes you go in a circle, okay? And it's up to you to identify what is that force, okay? So let's do an example. So let's suppose we have a 3-kilogram cat is whirled in a circle, of radius, let's say, let's say 1.2 meters. And we're going to say that the cat is whirled around once every 2 seconds. Okay? Once every 2 seconds, the cat is whirled around a circle. So I'm going to draw this. This is animal abuse. Don't ever do this. Okay. Here's the circle that the cat is being whirled around in. Okay. And what I would like to know is, what is the tension in the cat's tail? Okay, because that would be the role, that would be the centripetal force in this case. All right, that would be the centripetal force in this case, because it's the tail of the cat that is the thing. So when you want to figure out what is the centripetal force, which force is the centripetal force, you want to think about, what is the force that if I removed it, the cat would no longer be going in a circle. Okay, and obviously, if you, I'm not saying you should ever do this, don't ever do this, but if you were to snip the tail of the cat, it would no longer be moving in a circle. Okay, it would go flying. Okay, so it's the tension in the cat's tail that is the centripetal force. Okay, so I go to Newton's second law, net force equals ma. All right, and the acceleration is the centripetal acceleration. So if you recall, I actually have two forms of centripetal acceleration. They both will give you the same number, but I'm going to actually use the second version of it, 4 pi squared r over t squared. And the reason is that I can see that the cat is spun around once every 2 seconds. So that's basically telling me what the period is. Okay. So because I knew the period, this first equation for centripetal acceleration does not have t in it. So I'm just going to use this one. That makes it easy. Okay. The force that is playing the role of the centripetal force is the force of tension. So we have mass times acceleration, which is 4 pi squared r 1.2 over period squared, so over 2 squared. Okay. Crunch the numbers. And I get that the tension is 35.5 newtons. It's actually not a lot of tension. So I think the cat's going to be okay. All right. Wasn't that nice? One last point before we transition to the Zoom room is, what happens when the centripetal force is removed? Okay. So for example, what would happen if the sun just disappeared? The Earth is moving in a big circle around the sun. So what would happen if the sun just disappeared and there was no more gravity from the sun? What would we do? Okay. So actually what happens is once we remove the centripetal force, Newton's second law, the net force becomes zero, and we then have Newton's first law, which says that objects in motion stay in motion, okay? So if we think about it, your velocity is tangent to the circle. So once the centripetal force is turned off, you just keep that velocity and you just head off tangent to the circle in a straight line, okay? So basically what would happen is if we thought about the solar system, you know, here's the sun, and here are all the planets orbiting it at various locations. You know, maybe something like this. Here are all the planets. If the sun disappeared, then all these planets would just get launched off in random directions, tangent to the circle, wherever they were in their orbit at that particular instant. Okay? So that's what would happen. So you should know that when the centripetal force is removed, the object will continue in a straight line tangent to the circle. All right? Make sure you know that fact. For some reason, a lot of people think that you would go away from the sun, like in that direction. That's not true. You go tangent to the circle. Think about if you're throwing a ball. Okay? If you're throwing a ball, where do you release the ball? Because the ball is basically going in a circle, right? Do you release the ball when your fist is pointed directly at the person, the target? What would happen if I was throwing a ball and I threw it and I let it go right here? Wouldn't I just throw the ball straight into the ground, right? If I'm throwing, I want to actually release it up here because the tangent to that circle is towards you guys, all right? Towards you guys. So it always goes tangent to the circle. All right. So that's my lesson for today.